In this lesson, we're starting to look at evidence for shells. And by the end, hopefully, we will be able to define first ionisation energy and successive ionisation energy, explain the factors that influence ionisation energies, and predict the number of electrons in each shell as well as the elements group using successive ionisation energies. The energy needed to form positive ions is known as the ionisation energy. Ionisation energies provide evidence for a model of the atom in which electrons are arranged in shells. The first ionisation energy of an element is the energy required to remove one electron from each atom in 1 mole of gaseous atoms to form 1 mole of gaseous 1+ ions. It is a measure of how easily an atom loses an electron to form a 1+ ion. We're now going to sum this up on the next slide. We're now going to draw an equation to show how we see the first ionisation energy. So to start with, we need 1 mole of gaseous atoms, in this case sodium. We now need to form 1 mole of gaseous 1+ ions. So don't forget, the first ionisation energy is the energy required to remove just 1 electron from each atom. So we're going to have as well 1 mole of electrons. This has a first ionisation energy of plus 496 kilojoules per mole. The plus in front of that value is very important, and we'll find out why later on in the A-level. We can find the value of plus 496 kilojoules per mole in a data book. Negative electrons are held in their shells by their attraction to the positive nucleus. To form a positive ion, energy must be supplied to an electron to overcome the attraction from the nucleus and be able to remove that electron. Electrons in the outer shell are removed first since they experience the least nuclear attraction. The outer shell electrons are furthest away from the nucleus and require the least ionisation energy. This leaves our positive ion with a 1+ charge. The nuclear attraction experienced by an electron depends on 3 factors. The first factor is the atomic radius. The greater the atomic radius, the smaller the nuclear attraction experienced by the outer electrons. The second factor is the nuclear charge. The greater the nuclear charge, the greater the attractive forces on the outer electrons. The third possible factor is electron shielding, which is the repulsion between electrons in different inner shells. Shielding reduces the net attractive force from the positive nucleus on the outer shell electrons. So if we look at the sodium atom that is on the screen, there is 1 electron in the outer shell, and there are 10 electrons in total between that outer shell and the inner positive nucleus. Those electrons in between the outer electron and the positive nucleus are all negative, so they have an effect of shielding that positive charge from that outer electron, which makes it easier to remove. The more inner shells there are, the larger the shielding effect and the smaller the nuclear attraction experienced by the outer electrons. Successive ionisation energies are a measure of the energy required to remove each electron in turn. For example, the second ionisation energy of an element is the energy required to remove 1 electron from each ion in 1 mole of gaseous 1+ ions to form 1 mole of gaseous 2+ ions. So it doesn't jump straight from 0 to 2+. It goes in turn, so 1+, 2+, 3+, etc. An element has as many ionisation energies as it has electrons. So for example, lithium has 3 electrons and 3 successive ionisation energies. We can show equations to represent the first 3 ionisation energies on the next slide. So, not forgetting that we're using the element in the gaseous form, we're going to show lithium and its first 3 successive ionisation energies. As you can see, each successive ionisation energy is larger than the one before. As each electron is removed, there is less repulsion between the electrons and each shell will be drawn in to be slightly closer to the nucleus. As the distance of each electron from the nucleus decreases slightly, the nuclear attraction increases. More ionization energy is needed to remove each successive electron. Successive ionization energies provide experimental evidence for the existence of different shells. So sometimes you see a large increase in successive ionization energies. So for example, we can see a large difference here between the ionization energies of lithium, so the first ionization and the second ionization energies. This large increase shows the second electron has been removed from a different shell close to the nucleus with less shielding from inner electrons. So that first electron that was removed, the first ionization energy, that is a lot lower than the second because it is in a different shell. It has the shielding from the inner electrons, and that provides us with evidence for shells. We can demonstrate this in a graph as shown on the next slide. This graph is taken from page 41 of the OCR Chemistry AS textbook. The graph shows how the successive ionization energies of nitrogen provide evidence for the presence of shells, with the shell number being shown by the symbol N. You can see a large increase in ionization energy as the sixth electron is removed from the nitrogen atom. The successive ionization energies are reflecting the change from one shell to another as you get closer to the nucleus. If the electrons were all in the same shell, there'd be no sharp increase or jump in the ionization energies. So, just to finish off and round up what we've learned today, we've learned that the ionization energy is the energy needed to form positive ions, and they provide evidence for a model of the atom in which electrons are arranged in shells. There are three factors affecting ionization energy: the atomic radius, nuclear charge, and the amount of electron shielding. We've also seen that we have successive ionization energies, and the successive ionization energies, as shown in this graph, provide experimental evidence for the existence of different shells.